Fermat's little theorem is a statement from number theory, but you can prove it by using group theory. It's a statement about the divisibility of integers, and in particular about prime numbers. Contrary to Fermat's last theorem, the proof of Fermat's little theorem isn't that difficult, as long as you have some basic knowledge about group theory. Okay, let's take a look at Fermat's little theorem. It states, let P be some prime number. Then A to the power of P is congruent A modulo P for all integers A. That's what Fermat's little theorem is stating. A to the power of P is congruent A modulo P for all integers A. If you're not that familiar with congruencies, so that notation here, this here just means that P divides A to the power of P minus A for all integers A. So this here just means that here P divides A to the power of P minus A for all integers A. Let's take a look at an example. So let's set P is equal to 5, which is a prime number. Now Fermat's little theorem states P is equal to 5 divides A to the power of 5 minus A for all integers A. Let's check this by plugging in some integer values for A. So for A is equal to 0, A to the power of 5 minus A is equal to 0, 2. And 5 divides 0. So that is all right. For A is equal to 1, A to the power of 5 minus A is equal to 1 to the power of 5 minus 1, which is equal to 0. And 5 divides 0. So that is okay too. For A is equal to 2, A to the power of 5 minus A is equal to 2 to the power of 5 minus 2, which is equal to 32 minus 2, which is equal to 30. And 5 divides 30. So we have also checked that here. For A is equal to 3, A to the power of 5 minus A is equal to 3 to the power of 5 minus 3, which is equal to 243 minus 3, which is equal to 240. And 5 divides 240. So that's all right. For A is equal to 4, A to the power of 5 minus A is equal to 4 to the power of 5 minus 4, which is equal to 1024 minus 4, which is equal to 1020. And 5 divides 1020. So that's okay too. And so on. Fermat's little theorem states that it doesn't matter which integer values A you plug in. 5 will always divide A to the power of 5 minus A for every integer value A. We will now prove Fermat's little theorem by using group theory. So we want to show that for a prime number p, a to the power of p is congruent a modulo p for all integers a. To show this, we take a look at the residue class ring set P. You may already know that this here set P is not only a ring but also a field, because P is a prime number. Now we take a look at the group of units of set P, which we denote like that. Set P cross. That group of units contains all these elements of set P that have an inverse with respect to the multiplication on set P. And as the name says, the group of units together with the multiplication of set P forms a group. Because set P is a field, every element of set P apart from the zero element has a multiplicative inverse. That means the group of units set P cross looks like that. Because set P is a field, it contains all the elements of set P that are not the zero element. Therefore, the unit group contains P minus 1 elements. Now we will use a very famous theorem of group theory. Normally, it's one of the first theorems that are shown after starting with group theory lessons. It is called Theorem of Lagrange. One of the statements of that theorem is that a to the power of the group order of some finite group is equal to 1, where 1 is the unit element of that group for all elements A in the finite group G. If we use the theorem of Lagrange on the group of units set P cross, we get that A to the power of the order of set P cross is equal to 1 for all elements A in the group of units set P cross. The order of set P cross is equal to P minus 1. So we get that A to the power of P minus 1 is equal to 1 for all elements A in the group of units set P cross. If we multiply that equation here on both sides with A, the equation becomes true for the zero element too. So by multiplying A on both sides, we get that A to the power of P is equal to A, and that is true for all A in set P, so for the zero element too. The last thing we have to do is to translate that here in the language of number theory, but this here just means that A to the power of P is congruent A modulo P for all integers A. So the proof is finished. Okay, I hope this video could help you to understand Fermat's little theorem. If you liked this video, please consider subscribing to my channel. That would help and motivate me to keep creating videos.